All right. Friction problem. We got one right here. We're going to determine whether the block is in equilibrium and find the magnitude and direction of the friction force when the pushing force is 120 pounds. So let's draw this guy up, right? So here's the space drawing, right? Just the normal drawing of this. Right, then we'll do the free body diagram once we have a clear picture of what's going on. It's a squeaky marker. Right, this, we're told in the drawing this is 50 pounds pushing down. That's the weight. Right. This is not drawn to scale. That's 40 degrees in here, and this angle is 30 degrees. And we're also told that mu sub s is equal to 0.4, and mu sub k is equal to 0.3. Okay, so it's a friction problem, right? Remember, friction problems are static problems, right? Because we want to find whether or not this block is in equilibrium, right? So we hear equilibrium and we automatically, our brain goes to statics, right? Sum of the forces is equal to 0. So let's draw our free body diagram, right? So put it right here. So remember, free body diagram, we remove it from the ground, right? So I have something that looks like this, where this angle in here 30 degrees. And I am going to use my coordinate system to be angled at that 30 degrees. Right? And I'm assuming that positive is going down the track here, right? I'm going to have some, let me get rid of that for a second. I'm going to have some normal force, right, that's perpendicular to my block, 30 degrees. So I have some normal force, and I'm going to have a friction force, right? And we are assuming what? And we're going to assume that the friction force is going down the slope, right? I'm going to assume that friction is going down the slope. Now for equilibrium problems, it doesn't matter, right? You pick, and if you get a negative, then it just means that you chose the wrong way. But let's do it this way, right? And I'm also going to have the weight of the block and the pushing force, right? So let me draw this here, right? So I've got my pushing force, right? This pushing force is at 40 degrees from horizontal, right? 40 degrees from, I'm sorry, I drew that the wrong way. That's not 40 degrees from horizontal in the original. 40 degrees from parallel to the 40 degrees from parallel to here, right? Parallel with the slope. So that's 40 degrees. Now that looks like it's drawn to scale much better than it was before. It's still not great, but it's better. All right, so P, and P we're told in the problem statement, right, 120 pounds. And I've got some weight, right? Got this weight vector, right? But this is my coordinate system. So I really want to break this down into x and y, right? And I want to break this into x and y too. Let's start with the weight, right? So this is wy. This angle in here is 30 degrees, right? It's dictated by the slope that this is sitting on. That's going to be Wx down there. And this is Py. That's Px, right? And this, again, not drawn great, but this is going to be a function of your 40 degrees, right? Again, let me draw that better. that's important. Right, because that's not really x. X is this line, right? So this is px, and that's py, right? So now there's no confusion. That's the 40 degrees, right? And 40 degrees comes from my new x-axis that I've defined here. Okay, so that's what our free body diagram looks like, right? And that's the key to this problem, right? And we don't have a kinetic diagram because it's not, I mean, you could draw one, you just have zeros for everything, right? Because the acceleration is zero. We're assuming, we're testing to see if we're in a static equilibrium, right? So because we're doing statics, right? Overall, the equation that we're going to use is the sum of my forces is equal to 0. Okay? So I can write this in the x and the y direction. So I'll do that, right? I'll write this in the x direction right here, right? So sum of my forces in the x direction is equal to 0 is equal to what? Well, I've got negative px, I've got positive w sub x, and I've got positive friction. Right? Now sum of my forces in the y direction, that's 0. Well, I've got normal force, positive. I've got negative p sub y and negative w sub y, right? So looking at this, right, what are the things that I know? Right, and I'll plug some things in a second, right? But, so looking at this, I know P, right? I know P sub x and P sub y. I know W sub x, right? And W sub y. So I know these 4 things, right? We'll calculate those in a second. I do not know friction, and I do not know normal force, right? But I can calculate both of those from these 2 equations, right? So 2 equations, 2 unknowns, we're good to go. Right. So I'm going to make some room here, right? So I'm going to get rid of the free body diagram. Actually, I'm not going to get rid of the free body diagram. I'm going to make this into my free body diagram up here so we can have it while we're working. And we'll calculate some values. So, P is 120. Normal friction. Okay. So there we are. Right. Oh, and I put my angles in, right? 30 degrees. 40 degrees. Y and x. Okay. So let's start some of the forces. Well, let's calculate some things, right? Let's say. So P sub x is what? P sub x is just P times cosine 40, right? Which is 120 cosine of 40 degrees. So P sub y should be 120 sine of 40 degrees. W sub x is equal to 50 sine of 30 degrees, right? Because remember, that angle in there is 30 degrees. W sub y is 50 cosine of 30 degrees. Now this does not take into account any of the sines. This is just to get magnitudes, right? I already took into account the sines in my equations, right? So I'm just going to plug this in for P sub x, but I'll still subtract it. It'll be negative P sub x plus W sub x plus F, right? Okay. So I'm not going to calculate those. I'm going to leave them as is and write my equations, okay? So sum forces x equals 0. Well, let's start with y, actually. Let's start with y. We're going to need the normal force before we start with x. This, right, is equal to 0 is equal to n minus P sub y, which is 120 minus W sub y, which is 50 cosine of 30 degrees. And so, we solve this for n, and my normal force comes out to be 120.44 pounds. So, before we go on, we need to review the friction criteria, right? So, if my frictional force is greater than my pushing force along the slope, right? In the same direction, right? So, if the component of my pushing force that's in the same direction as my friction force, right? So in this case, X. So if F is greater than p sub X, then what? My friction force is greater than my pushing force, then I don't move, right? If F is equal to p sub X, then I have impending motion. And this is really F max, right? Let's call this F max, sorry. And if my maximum friction is less than my pushing force in the X direction, then motion, right? So these are my criteria. Well, how do I find F max? Remember, F max is equal to mu sub S times my normal force, right? It's mu sub S times my normal force. And this is the part that's probably going to be tricky, right? You don't just plug in mu sub S times my normal force or mu sub K times my normal force, right? You're checking your pushing force against this. Because remember, if I was to draw a plot, right, of friction versus my pushing force, right? Friction versus my pushing force. I will have something that looks like that, right? It's linear until it reaches the maximum, and then it drops to its kinetic friction level, right? Okay, so now that we have this, right, written down, let's calculate what our frictional force comes out to be, right? Let's calculate F max. We'll calculate F and then we'll calculate F max, okay? So if I'm going to sum my forces in the X direction, that's equal to 0. And that's going to say that negative 120 cosine of 40 degrees plus 50 sine 30 degrees plus F, right? So I can solve for my frictional force, and my frictional force with these numbers is 66.93 pounds. So 66.93 pounds, right? Okay, but that's not the number that we are checking against, right? We need to check F max, not F, right? What's F max? Mu sub S times the normal, which we don't have written up there anymore, but that is 0.3. Mu sub S is 0.3. Sorry, no, mu sub S is 0.4. Mu sub K was 0.3. 0.4 times my normal force, which is 120.44. So my maximum friction is what? 48.17 pounds. But you said that we calculated friction to be 66.9. How can the maximum be less than that? Well, you're going to see why the maximum is less than that. Well, this is the maximum, right? So this friction cannot be 66.9. It can't. right? Because that is the maximum friction that we have. Remember, friction describes the forces between two interfaces, right? Whatever the block is made out of and whatever the slope is made out of, right? How they interact with one another. So what happens when we check Fmax with our pushing force in the x direction, right? Our pushing force in the x direction is 120 cosine 40, which is down here. P sub x is equal to, when I crunch this, 91.93 pounds. 91.93 is larger than 48.17, and therefore we have motion, right? Based off of this, Fmax is less than Px, but this was also larger, right? So we kind of had an idea that we were going to be moving anyway, right? And if we find out that we're moving, we have to calculate our actual friction, right? And how do we calculate our actual friction? Let's do that. Clear some room. Get rid of this. Motion, yeah. It's not static anymore. So my actual friction, since I know I'm moving, is mu sub k times n, which is 0.4 times 120.44. So my actual friction is 36.13 pounds. And that is at 30 degrees to the horizontal, right? All right, along the slope. So 36.13 pounds. Okay. So that's the basics of it, right? When you're asked to find friction, you're asked to find whether or not something is in equilibrium, right? Start with the free body diagram. Use your statics equations, right? Calculate what your Fmax is. Compare Fmax to the pushing force in the same direction as your friction force, right? If Fmax is greater than Px, then you don't have any motion, and what you calculated here for F is your friction, right, as it balances. If Fmax is equal to your pushing force, you still haven't put enough in, right? You're right at this point on the graph. You're just about to move, right? So if you have impending motion, that means that your pushing force is equal to Fmax, right? Or that Fmax, that your friction has to equal 48.17 in this case, right? And like we found, if Fmax is less than Px, right? If your pushing force is greater than your maximum friction, then you're moving. That's what it's about. Cool?